Number of observed fringes. To determine the number of bright and dark fringes, it is the path difference equation that calculates this number. So the path difference is d sine theta mc lambda, or d sine theta md plus 1/2 lambda. This is for constructive, this is for destructive. If I solve for the sine of theta in each of these cases, this sets the condition for the number of fringes. If you look at both of these equations, they're proportional to the wavelength divided by the slit separation. But the slit separation and the wavelength are constants in problems. So therefore the sine of theta is proportional to mc, or the sine of theta is proportional to md. That is the number of bright and dark fringes. The way we use the fine is that the sine function only makes sense if sine of theta is less than or equal to 1. And it's mathematical nonsense if it's greater than 1. To determine the number of fringes, we sum the sequence of m terms until one violates it. That is, we take this equation and we start setting in mc equal to 0, 1, 2, 3, and we go until the sine of theta is greater than 1, which then stops the sequence. But then that gives us our m value. As an example, suppose d is equal to 3 lambda. And we want to determine the number of bright fringes for a two-slit interference setup. It is the path difference equation that determines the fringe number. Starting with the path difference equation, I solve for theta, sine of theta, and then I put in lambda over d, which is 1/3. So the main equation here is sine of theta is equal to 1/3 m. Next, we now sum the sequence by setting mc equal to 0, plus or minus 1, plus or minus 2, etc., until sine of theta is greater than 1. So the first term is mc equal to 0, and then the second term is 1, 2, 3, 4, and if I add those all up, and you can see here, all the first 4 terms are less than or equal to 1, but this last term is 4/3, and 4/3 then cannot exist, since this implies here that sine is greater than 1. Since our m value was at 3, that tells us that mc is equal to 3, so the number of bright fringes is equal to 1 plus 2mc. 1 because we have the central max, which is at mc equal to 0, and then 2 because they're symmetric about 0, so I get the plus and minus sign. So this tells us that this interference pattern has 7 bright fringes. We can also calculate the number of dark fringes using the same procedure. So sine of theta is equal to md plus 1/2 divided by 3. So if I follow the sequence for md, I have 0, 1, 2, 3, but they're symmetric, so there's always plus and minus signs. And what you're seeing here is this guy violates it, since this sets sine of theta greater than 1, which then tells us that md is equal to 2. So the number of dark fringes is 2 plus 2md. And what you're seeing here is that the 2 here is because there are 2 terms that are md equal to 0. And then again, 2 is because of the plus minus. This means then that there are 6 dark fringes. So there are 7 bright and 6 dark fringes. What does that pattern look like? So I have 7 bright fringes, so I got the central, plus I got 3 on each side. And if I label all of the mc values here, you could see that I got 1, 2, 3, minus 1, minus 2, minus 3. So now I add the darks. So note that I have to separate the darks, symmetrically. So then I have 1, 2, 3, 1, 2, 3. So if you look at md, I have my 2 zeros, and then I'm symmetric about 1 and 2. Here's 1 and 2, and then minus 1, minus 2. So you could see here that the ends are bright spots. Let's go to an interference applet to see this type of interference. So here is the interference applet, and one of the numbers that we really want to look at is we want to look at d divided by lambda. So in our case, that was 3. So if I click this to 3, I'm going to get to 3.07. So let's go count them. we said that we had 7 bright fringes. So here I go. So if I go smack through the middle here, what you're seeing here is that this guy is MC equal to 0. So then I go MC equals to 3, then gives me 1, 2, 3. So therefore that gives me 3 on this side, 3 on this side, plus 1. That gives me 7 bright fringes. Now if I look at the dark fringes, we had MD equal to 2. So here's 0, 1, 2. So that's 3 on the left, and therefore 3 on the right, which gives us 6 dark fringes. So this is agreeing with what we just calculated. The intensity for two-slit interference. Suppose that a single light source is shining onto a screen. The intensity at the screen is computed by the square of the amplitude. So the intensity of a single source, which is depicted by I0, is the amplitude squared, and the amplitude squared here is the strength of the electric field squared. If two sources are shined onto a screen at the same distance, the overlapping interference pattern is, the intensity of two sources, which I'm going to label IM, is going to be the square of the amplitude, so it's going to be 4 times the intensity of a single source times this cosine squared 1/2 phi here, which this is really the phase issue. Picture-wise, here's what this all means. So if I have a single source, the intensity of the peak is I0. Now imagine that I have two sources that do not interfere. So I essentially have two light sources shining on a screen simultaneously. That is not once I0, but twice I0. But if I have two sources that do interfere, the intensity is not twice as much, but 4 times as much, which is super counterintuitive. And it really comes down to the meaning of what we mean by interference in the language of energy. Question: why are two sources that interfere twice the value of intensity than two sources that do not interfere? This is because of conservation of energy for waves. Interference moves energy from destructive interference regions and transfers it to constructive regions, making the peak intensities twice as high. So as light goes through the two slits, they only redistribute the energy then. The intensity equation is usually written in the language of the phase and the path difference. Starting off with these two equations, we then rewrite 1/2 phi as follows. So 1/2 phi is equal to pi d divided by lambda times sine theta, and this is typically defined as this beta factor. This beta factor is a phase factor for two-slit interference. The intensity equation then reads that the intensity of the two-slit is then going to be 4I0 cosine squared beta, where beta is then again pi d divided by lambda sine theta. So if I look at the intensity function one more time, we have our central fringe. That's labeled by MC equal to 0, beta equal to 0, and the path difference equal to 0. So if I go to the right, then I'm going to get MC equal to 1, 2, 3, which means that beta then must have a phase of pi, 2 pi, 3 pi. If I look at the path difference, it's got to be lambda, 2 lambda, 3 lambda, and then of course it's symmetric between the right and the left. Example 33A.3. Suppose a radio station operating at a frequency of 60 megahertz has two identical vertical dipole antennas spaced 10 meters apart, oscillating in phase. The intensity at a distance of 700 meters in the positive x direction for a single antenna is I0 equal to 0.02 watts per meter squared. A. What is the mathematical expression for beta? And the intensity is a function of theta. B. How many dark and bright fringes are in the pattern? What are the angular locations of the bright and dark fringes? And draw a picture of the situation. What is the relative intensity at 4 degrees, and where is that located? A single antenna has intensity of 0.02 watts per meter squared. These antennas are separated by a slit separation, little d, which is 10 meters. Because these are radio antennas, they emit radio waves with wavelengths that we need to calculate. That is, the wavelength is equal to the speed of light divided by the frequency, the speed of light being 3 times 10 to the 8 meters per second, and the frequency here is the frequency of the antenna, which is 60 megahertz, or 60 times 10 to the 6 hertz, which tells us that the wavelength is equal to 5 meters. The interference parameter d over lambda plays an important role in determining how much interference is going on when two sources are interfering. In this example, we see that d over lambda is equal to 2. Now let's go put this into the interference equation. The intensity equation reads as follows. So my intensity for the two slits then is 4 times the intensity of the antenna times cosine squared of beta, but beta is pi d over lambda sine of theta. Putting in my value for the antenna, putting in my value for d over lambda, I end up with 0.08 watts per meter squared cosine squared of 2 pi sine theta. B. Now we need to determine the number of dark and bright fringes. Dark fringes occur when the intensity is 0. So I'm setting the intensity of the two slits to be equal to 0. What this means, though, is that 0 has to be cosine squared of 2 pi sine theta. That's the only way this could be 0. So now I focus on the cosine squared term. This means then that cosine of 2 pi sine of theta must be equal to 0, but the only way cosine could be 0 if it's odd multiples of pi over 2. Once again, cosine can only be 0 if you have odd multiples of pi. So therefore the argument of 2 pi sine theta can be plus or minus 1/2 pi, plus or minus 3/2 pi, plus or minus 5/2 pi. And if I summarize that, then it's going to be md plus 1/2 times pi. So now I solve for sine of theta. So if I focus on the first term of 1/2 pi, if I divide that by 2 pi, I get plus or minus 1/4. If I do that to 3/2 and 5/2, you'll see that I'm going to get 3/4, and then I get 5/4. This guy is not possible because now this means that sine of theta is greater than 1. This tells me then that there are going to be 2 dark fringes on each side, so therefore MD must be equal to 2. This tells me that MD must be equal to 1. If MD is equal to 1, then the number of dark fringes, which is 2 plus 2MD, then gives us 4 dark fringes, exactly what we just expected. We then apply the same procedure for bright fringes. The intensity equation, cosine squared, has to be maximal in order to have a peak intensity. Cosine is maximal at plus or minus 1. The only way this could be true here is if the argument is multiples of pi. So therefore 2 pi sine theta must be 0, pi, 2 pi, 3 pi, etc., which we could summarize as plus or minus mc pi. Using this equation to solve for sine of theta, I then get 0 over 2 pi, pi over 2 pi, 2 pi over 2 pi, 3 pi over 2 pi. And you could see here is that this guy exceeds sine of theta greater than 1. Therefore, MC must equal to 2. So the number of bright fringes should be 1 plus 2MC, which then gives you 5 bright fringes. So what does the interference pattern look like? So according to this picture here, I have my 2 sources that are separated by 2 lambda. So for MC equal to 0, that's where the path difference is 0. And then I have 2 bright fringes, so I go MC plus 1, MC plus 2, but MC plus 2 is at 90 degrees, and then I go MC minus 1, MC minus 2. And then if I look at the dark fringes, I have 2 dark fringes on both sides here, so I got MD equal to 0, MD equal to plus 1, and then on the bottom I get MD equal to 0 and MD equal to minus 1. So what would it look like on the screen? Well, I would have 5 bright reds and 4 dark blacks. So let's check this out on the interference applet. So right now I have d over lambda that's equal to 3. That is my interference parameter. So now what I need to do here is that I need to reduce that down to 2. So let's go down to 2. And what you're seeing here, now I'm at 2, so that means that the path difference between that source and that source is 2 wavelengths. So let's count them. So I got the central fringe right here. Then I have 1, 2, and then 1, 2. So I have 5 bright fringes. And then you could see here that I have 2 dark fringes on both sides, just as we saw beforehand. C. What is the location and intensity at theta equal to 4 degrees? To determine the location, we need to calculate the phase factor beta. So what I do here is that I don't compute the value of pi, but I plug in the values for d, lambda, and sine of theta. So when you compute that, you get 0.14 pi. For beta, this tells us the location. Going to the intensity patterns, this is what we know about the angles. This tells us that this is 0 degrees, and these two are 90 and minus 90. So when I come over here, you could see that the farthest to the right is plus 90, farthest to the left is 90. So where is 4 degrees? If I look at the beta factor, I have 0, pi, 2 pi, minus pi, and minus 2 pi for the maximas, and the dark fringes are located at pi over 2 intervals. So for theta equal to 4 degrees, beta is 0.14 pi. For theta equal to 4 degrees, we know that beta is equal to 0.14 pi. So if I look at the central fringe, that's 0. If I look at the first dark fringe, that's 0.50 pi. So therefore, that 0.14 pi is in the maximum of the first central fringe. So then beta 0.14 pi is closer to the maxima than it is the minima, but it's in between these two fringes. That's the location of where that theta equal to 4 degrees. Now let's go calculate the intensity. The intensity at 4 degrees is then written in terms of beta, so it's 0.08 times cosine squared of 0.14 pi, and numerically this value is 0.064 watts per meter squared. Unfortunately, that's not the way we want to write it. Relative intensity is the most important, so we then write that the intensity at 4 degrees divided by the intensity at 0 is defined as the relative intensity. This is always equal to cosine squared of beta. And what we're getting here is that the relative intensity is at 82%. Now going back to our picture, at the peak intensity, this is 100%. So where is this 4 degrees? It's at 82% of the maximum intensity.